Hey everybody, so today we're going to be talking about a little extra variation here about weak acids. And what we're going to talk about today is the percent dissociation and some information about polyprotic acids. Now, percent dissociation doesn't only work for weak acids, it also works for weak base. But little variation here on rather than just finding the pH. So here we go. So what you'll see when you hear the term percent dissociation, it's the how much breaks apart. And we know for weak acids and weak bases, that's a very small amount, hence their definition of being weak. Whereas a strong acid or a strong base, that percent dissociation is 100%. So the definition here of the percent dissociation is the concentration of either the acid or the base and how much of it dissociates over the concentration of the acid or the base that you had initially, and then for a percent times 100. So how much falls apart? And usually we're talking about very small amounts, a few percentages, because they're weak acids and weak bases. So now let's try to see if we can apply this to an example. First example, what is the percent dissociation of 0.050 molar aqueous solution of HC2H3O2? That's actually acetate with an H, so this is acetic acid. And first question you should always ask yourself again with these problems is, what is this? Is it an acid or a base? Is it strong or weak? And look what clues you have. They gave me a pKa, so that should give you a hint. This is a weak acid. So my weak acid, it's going to react with water. It's going to make H3O plus and that leftover conjugate base. I can fill in an ice table, but I know how these go, so I don't want to do an ice table right now. I know water doesn't need to show up. I know the amount of H3O plus is about 0. I can fill in my X's. I can do all that, but we're going to skip from there and go straight to here. Where we know that the Ka is going to equal X times X and 0.050 minus X. So we can skip the ice table and go here. We need to get Ka. We have pKa. And remember, P of anything is minus the log of that. So then Ka is 10 to the minus pKa. So 10 to the minus 4.74. And I get my Ka as 1.8 times 10 to the negative 5. Plug that in here, we'll solve for X. I don't want to do a quadratic. We'll make that assumption that the X is so small that when you subtract it from 0.050, it will not change the value of 0.050. So then I'm only doing a square root. I solve for X, and I get a value of 9.5 times 10 to the negative 4, which we should go check and make sure that assumption works. In this case, I'm going to skip the check. It does work in this case because we're asked to find the percent dissociation. So I want to know how much acetic acid dissociates over how much acetic acid we had at the start times 100. All right, to figure out how much acid dissociates, that's how much product we made. And how much product we made, that's my X. That's how much of the acid fell apart. So that's 9.5 times 10 to the negative 4 over the amount of acid I had at the start. Well, that was given in the problem, 0.050 times 100. And we get that it's 1.9% dissociates. The other thing to notice here when you're doing this percent dissociation calculation, it's the same check that we've been doing to see if the assumption works. So as long as we're within that 5%, we can ignore that little X in the denominator where we're subtracting. That same assumption is percent dissociation. And again, it's a weak acid, so only less than 2% of it dissociates. Hence, it's a weak acid. Now let's try a variation of another weak acid problem. And we're going to work with what's called a polyprotic acid. So polyprotic, remember, means more than one H can be donated. So in acetic acid, there were more than one H in the formula, but in terms of how many were donated and were acidic, there was only one H that's acidic. If it's a polyprotic acid, there is more than one H that can be donated. So in this question, we're asked to calculate the pH and the concentration of all species present in H2CO3. Again, first question, what is that? Acid or base, strong or weak? And it turns out H2CO3 is carbonic acid. This is a weak acid. And since it's a weak acid, we're going to need a Ka value to figure out how much this acid dissociates to know how much H3O plus it makes. Well, if you look in a table for H2CO3, you're going to find two Ka values. You're going to find Ka1 and Ka2. And Ka1 I found was 4.3 times 10 to the negative 7, and Ka2 was 5.6 times 10 to the negative 11. So what this means is H2CO3 has two H's to potentially lose, which means there's two sources of acid coming from H2CO3, which means we need to do two ice tables. So in this case, I will write out the ice tables since we're going to do two of them. So the first one, H2CO3, again, the only thing it can react with is water, makes H3O plus. HCO3 minus is the conjugate base. Remember, you only take one H off at a time. That's what Ka1 represents. Initial change. Water doesn't matter. The initial concentration was 0.020. About 0, we're going to assume the amount that comes from the autoionization of water is something we can ignore. 0 minus X plus X. And then this is all for Ka1, losing of the first hydrogen. So I know 4.3 times 10 to the negative 7, it's going to be X times X, 0.020 minus X. Make that assumption because I don't want to do a quadratic or successive approximations. And then ultimately we can find that X equals 9.3 times 10 to the negative 5. Before we go any further, let's check that this assumption is okay. 9.3 times 10 to the negative 5, that was how much I lost, divided by how much I started with, times 100. And we're at about 0.4%, so well within that 5% threshold. So we found out how much H3O plus we can get from H2CO3. Now the hiccup is this can then lose another H to make potentially more acid that we need to account for. So we're going to need to make a second ice table where my starting acid now is the conjugate base from before. Again, the only thing it's going to react with is water, still to make H3O plus. And now we're going to go to the conjugate base of HCO3 minus. This is the Ka2, the removal of the second H. Ice table again. The concentration of HCO3 initially goes right there. So that will be my 9.3 times 10 to the negative 5. The concentration of carbonate, that's 0. I don't have any of that. The concentration of H3O plus at the start, it's not about 0 here, because at this point I have H3O plus from water, which we're going to ignore, but I also have H3O plus from the previous reaction. So this is going to be 9.3 times 10 to the negative 5 also. I still don't have any carbonate present, so this reaction must go forward to make carbonate. So we're going to go down. I'm going to call it Y in this case, just to change up the variable. 9.3 times 10 to the negative 5 minus Y. 9.3 times 10 to the negative 5 plus Y and Y. We can plug that into my Ka2 expression, which was 5.6 times 10 to the negative 11 equals 9.3 times 10 to the negative 5 plus Y times Y. 9.3 times 10 to the negative 5 minus Y. And you should be saying, ew, gross. That's definitely still doable with a quadratic, just a lot of work to get it even into the potential formula to then plug into the quadratic. So let's see if we can do some assumptions to maybe neaten up the math here. So down here, we've done this assumption before. We know the k value is very small, which means we're going to have very little product, which means y is very, very small. And if y is very, very small, 9.3 times 10 to the negative 5, that's the same thing as 9.3 times 10 to the negative 5. Sorry, 9.3 times 10 to the negative 5 minus y is the same as 9.3 times 10 to the negative 5. Well, if that works down here, that also will work on the top. If y is such a small number that when you subtract it, you will not change the original number, then when you add it, you will also not change that original number. But this y out here on the end that is multiplied, because it's multiplication, whether that number is big or small, it will have an impact. Hey, look at this algebra. So 5.6 times 10 to the negative 11 equals y. We've discovered our answer. So then now the last piece here is to answer the question, what is the concentration of all species present? Okay, well, let's make a list of what's around. We have H2CO3, my original acid. We have the conjugate base of that acid when it loses one H. We have the conjugate base of that new acid when it loses a second H. We have that acid once it's been protonated, the water's been protonated. There's water, of course, and don't forget if there's one of these present, then there are some of those present. So let's see if we can figure all these pieces out. So H2CO3, go back to your ice table, find H2CO3. H2CO3, it turns out, is right there. 0.020 minus x. 0.020 minus x, so 0.020 minus that 9.3 times 10 to the negative 5. So just like we found, basically it remained unchanged, 0.020. HCO3 minus, well, it was a product in the first and then a reactant in the second. So the amount of HCO3 ultimately ends up being right there. 9.3 times 10 to the negative 5 minus y. So 9.3 times 10 to the negative 5 minus that 5.6 times 10 to the negative 11. So it remained unchanged from the first step. Now, carbonate, CO3 2 minus, that only was generated in the second reaction, and that was found to be y. So there's a little bit of that. The H3O plus, there was some generated in the first reaction, which we then brought down to the second reaction. So ultimately, this is the amount of H3O plus we are left with. So the 9.3 times 10 to the negative 5 plus y, 9.3 times 10 to the negative 5 plus that 5.6 times 10 to the negative 11. So 9.3 times 10 to the negative 5. And then the OH concentration, we're going to get that relating back to how much H3O plus we had. So 1.0 times 10 to the negative 14 divided by how much H3O plus, 9.3 times 10 to the negative 5, for a total of 1.1 times 10 to the negative 10. Not surprising, it's very small. This is a weak acid, so we expect there to be more H pluses than we do OH minuses. And then finally, the last piece was to find the pH. Minus the log, how much H plus, 9.3 times 10 to the negative 5, and we get a value of 4. Again, hopefully it makes sense. It's a weak acid, so we should be below that threshold of 7, and we are, and there we go. Polyprotic acids. thing to sort of note here is notice that primarily it's the first losing of the H that provides the bulk of the acid. The second one, it happens, but with the big discrepancy between the two Ka's, it doesn't happen nearly as much. So there you go, another variation. You can do the same math that you would if you had a base that could accept two H pluses, same process. There we go.